Okay, our next speaker is Dr. Karl Stapelfeldt, one of NASA's chief scientists for the search for exoplanets.
All right, well, I'm very pleased to be invited to the convention this year. I'm a longtime Mars exploration fan and follow what's happened from the outside. But I think I'm the first speaker you've ever had to talk about the broader context of planets around other stars to go along with the great planets that we have in our own solar system. So this is an area that has become very much more active in the past 30 years, where in the early 90s, we basically didn't know there were any exoplanets for sure at all. And now we have thousands and thousands of them, and a growing fleet of spacecraft that can work to characterize these. All of them, though, are remote observers, telescopes, like the Mars Reconnaissance Orbiter telescope from orbit, looking down and taking spectra and seeing details. That's the kind of perspective we have here. So I want to just give you an introduction to the exoplanet field, what NASA is doing now and what we hope to do in the future. So here's the overview of the talk. I'm going to talk about the ways we detect exoplanets, what we know today from all the detections so far, point out a couple really interesting individual planetary systems, but in truth, there are dozens that we could talk about. And the upcoming and proposed exoplanet missions could be particularly important soon for reasons I'll explain. And then I'll tell you what our program does and how we got to be where we are. So here we go. So there are multiple ways to detect an exoplanet. Most of them are indirect. This means we have to watch what the star is doing because we can't see the planet itself. And the star can be perturbed by the planet in a number of ways. And one of them is just by the total brightness of the star varying with time. Most of the time it's completely constant. But if there's a planet whose orbit is aligned exactly edge on to our line of sight, that planet will pass in front of the star and give us a transit signal where the star's light is diminished, as the animation just showed. And so if it's a larger planet, we get a larger dip in the star's light. A smaller planet gives us a smaller dip, and that gives us the opportunity to measure the size of the planet relative to the size of the star. And then by the time it takes for these transit events to repeat, we can immediately observe the orbital period of the planet. And therefore, with Kepler's laws, work out the distance it is from the star, and therefore what its temperature is. This is best done with space telescopes because the planet makes a very small perturbation on the brightness of the star, only 1% for the Jupiter passing in front of the sun, and 0.01% for the Earth passing in front of the sun. The radial velocity method is done mostly from the ground using telescopes with high precision spectrographs. In these cases, we're watching the star orbit around the center of mass of the star-planet system. And as the star moves away from you, as I hope the bandwidth is showing now, the light from the star will be redshifted, as the animation is showing. And then as it moves around to come towards you, the star's light will be blue shifted. But this is by very small amounts. We're seeing the star's velocity change by sort of 1 to 10 meters per second. Yet we can observe that with sufficiently large telescopes and sensitive instruments. And this is what was really effective in the early days for discovering the first planets around other stars, solar type stars. So those are the top two methods, the transit method affecting the star's brightness and the stellar radial velocity. I checked yesterday at our NASA Exoplanet Archive, and we have 4,527 confirmed exoplanets. The answer will be different next week. Most of these are transiting planets that pass in front of the host star because those are easy to detect. You don't really need any specialized equipment except being able to measure the star's brightness. But there are multiple other more arcane different ways of measuring the planet's presence around the star. And the one that's most intuitive, direct imaging, where we just see the planet as a point of light. We do not see it as a resolved disk the way we're used to seeing the planets in our solar system. That's only about 54 planets, not the thousands that transit has detected. And even many of those 54 might have large enough masses to be called brown dwarfs, which for astronomers are a Jupiter-like planet that got so big that it started to have fusion inside its core, at least temporarily. So we've got many different approaches for detecting exoplanets, all with different strengths and weaknesses. So the Kepler mission that I hope you've heard of was launched in 2009 and concluded in 2018. It was NASA's first dedicated mission to try to find planets around other stars. So it used the transit method. It looked simultaneously at 150,000 stars continuously for 3 years straight, with the idea being that if you saw a 1-year period planet, its transit passing in front of the star should repeat 3 times, and therefore you could confirm that you had a real detection. So Kepler detected almost 3,000 confirmed exoplanets plus a whole bunch more candidates. And it had some very important results on defining the field. First of all, it found lots of multi-planet systems that are 2, 3, up to 7 planets orbiting in the same plane, the very flat plane passing in front of the star. And it showed that there were lots of planets at very short orbital periods, planets inside the orbit of Mercury, if they were in our own solar system, were the dominant kind of planets that Kepler found. Those were the easiest for it to detect because the orbits would repeat many, many times and improve the sensitivity. Kepler was able to measure the frequency of small planets in this liquid water habitable zone, the Goldilocks zone, where it's not too hot so that the water ocean would evaporate, not too cold so that it would freeze, but where it's just right, and found that maybe 25% of all the sun-like stars it observed had a habitable zone planet of one sort or another, although there's a large uncertainty on that measurement. And it very critically observed the size distribution of planets. So let me show you here the statistical results from this. The graph shows how on the horizontal axis, the size of the planet is plotted. On the vertical axis is how often they're seen. And what's important to note here is that there really are 2 peaks in the size distribution. There's one about 1.5 Earth radius. There's another peak at about sort of 2.2 Earth radii, with a gap in between at 1.7 where there are fewer planets. And most intriguingly, there are so many different planets detected between 1 and 4 Earth radii. 4 Earth radii is special. That's the radius of Neptune. So most of the planets that Kepler saw are in the size range where we have no example in our solar system. In our solar system, there's Earth at 1, Neptune at 4, and nothing in between. Well, here's a whole different kind of planet that we call super Earths and sub-Neptunes that fill in this gap. And we believe what's happening here to create this gap in the distribution is that if you have an atmosphere on a planet that's not got enough mass, it can't be retained. But once you get massive enough to be a sort of a 2.5 Earth radius planet, you can also retain a hydrogen envelope. And so that's what's accounting for this feature. So there's another way of plotting the number of discovered exoplanets, and now this is by mass instead of size, and also by orbital period across the horizontal axis. And what's interesting is that these planets are not spread over just anywhere in the diagram. They tend to fall in clumps. So you can see that we have a green clump of transiting planets near 1 Jupiter mass and a few days orbital period. Those are what we call the hot Jupiters, which were a total surprise when they were first discovered, but it was actually the first exoplanet around a sun-like star was a hot Jupiter. We think these are planets that form further out, maybe where our Jupiter is, migrated in, and then their migration stopped at orbital periods of a few days. Then we see another pile up of planets detected by radial velocity in red, and this is more the Jupiters that are in the formation region we expect of a few AU. And then lastly, there's a clump down at the lower end where we start to see the smaller planets, most of which are the few Earth radii planets that I just talked to you about. The imaging method has very few points on this chart, but you can see that they're detected, planets by imaging are detected only at wide separations because it's hard to look in close to the glare of a bright star. That's the direct method. The others, of course, are indirect. So in terms of notable planetary systems, and I hope you may have heard about, TRAPPIST-1 really stands out. This is a very ultra cool red dwarf star, not that far away from the sun, and it has 7 planets that were found by the transit method, at least 3 of which are in this habitable zone where liquid water could persist on the surface. And in 2017, this discovery was announced. It made above the fold news in the New York Times. So the thing is, they're all Earth-sized planets, and they all can be characterized with transit and with, as you'll see in a minute, spectroscopy. So this is a tremendously exciting and rich system. We don't know if there's atmospheres around these planets yet, but JWST is going to be able to tell us about that. Then Proxima Centauri, you may know, is the nearest star to the sun. It's another red dwarf. And the radial velocity method, with the graph shown at the bottom right, is able to detect the star's velocity changing. And there's lots of error bars on the points, so you can see that it's not a high signal to noise detection, but it's still good enough to believe. And so this is a roughly Earth mass planet in that star's habitable zone. And we don't know if this one has an atmosphere either. So altogether, in terms of small planets, there's 165 planets in our database that are Earth-sized or smaller, and for you Mars aficionados, there are 4 known planets that are Mars-sized or smaller. That's not because Mars-sized planets are rare, it's because they're hard to detect. If we had better detection methods, I bet you we would see many, many more small planets than we're currently able to catalog. So we want to do more than just find that these planets exist and measure their orbits or sizes or masses. We want to know about their atmospheres, because that is what's crucial for being a truly habitable planet and supporting life. And in terms of studying the atmospheres, spectroscopy is the key tool, just like it is for studying mineralogy of Martian surface rocks or the Mars upper atmosphere. And so here's the spectra, relatively low resolution, of Venus, Earth, and Mars. And I'm sorry to reduce your favorite planet here to just one line. All the details about it, all the great geography and so forth is reduced to one line, the reflectance spectrum of the planet. And the visible is over here on the left-hand side, visible light. And mostly we're seeing infrared, near-infrared light across here. Well, Mars barely has an atmosphere, so we don't see very strong features from the gases in it. The continuum level here is relatively unchanging. Earth, however, has both water vapor absorption and molecular oxygen absorption that are very prominent in its spectrum. And so those are indications that it is a habitable planet, that we want to be able to see if other planets around other stars might have similar features. Venus shows different features, with CO2 dominating the absorption spectrum. So this is the kind of data that we really want to get for exoplanets, because for those 4,000 planets I talked about, the ones with spectra are a vast minority out of them, and we really seek to change that to enter the era of exoplanet characterization. So there's 2 ways to get the spectrum of an exoplanet. You need to collect photons from the planet. It's not enough to just see the star being perturbed by the planet. So you can have the planet illuminated sort of from the front, and you're seeing it like a fully illuminated phase, or it can be illuminated from the back. And let me try to illustrate that with a couple of things that aren't planets. First, this cloud in the sky, you're seeing all the light reflected off the front surface. But if you look at the silver lining of the cloud, when the sun is behind it, there's light passing through that silver lining, and the particles in the cloud can impose a spectroscopic signal on the sun's light and let us know something about the composition of that cloud. Well, the same thing is true for me. Here I am at the test launch, seen illuminated from the front. You look like a regular person. When I'm illuminated from the back, you see my silver lining. I wish it wasn't quite so silver, but years get on. But the more important thing here is that here's Titan seen as front illuminated, and when Cassini was positioned to have Titan between it and the sun, and Venus fully illuminated, and when Venus is starting to cross the disk of the sun. And there's this very tiny sliver of atmosphere around Venus where sunlight is passing through, and that sliver is enough to give us a chance to detect the spectrum of the gases in the planet's atmosphere. So this is a spectrum we would take by transit, and up here is a spectrum we would take by direct imaging. The disadvantage of the transit is that unlike the Titan case, Venus is very much smaller than the sun, and so we're unable to get rid of the sun's light. We're measuring Venus's spectrum at the same time as we're collecting all this glaring light from the sun. So for exoplanets, JWST is going to use this transit spectroscopy method, the backlit way of measuring light passing through the planet's upper atmosphere. So here, James Webb Space Telescope, I'll talk more about it in a minute. Here's some simulations of what it might be able to see for a large exoplanet. This would be a hot Jupiter. And so it's predicted, measurement points are shown here. You can see that water vapor signatures are very expected to be easy to detect, also a little bit of carbon monoxide. And there's a lot of complexity depending on which constituents you include in the spectrum model and which filters you're using on JWST. But for a small planet, like in the TRAPPIST system, this is the simulation of what you'd be able to do. And it's much closer to the noise because it's harder to detect that small planet. But we may be able to detect water vapor in that planet and especially carbon dioxide in the TRAPPIST planet. So really look forward to JWST getting a chance to make those measurements in a couple of years. The thing to notice here, though, is that because we're collecting all the light from the star at the same time as the planet, they're not separated. The signal levels here are measured in ppm, parts per million. So these variations in the strength of the spectral features are only corresponding to like 50 parts per million of the total light of the star, and they only take place when the planet is passing in front of the star, of course. But nevertheless, JWST is our first real bite at measuring the spectra of small planets around other stars. And I hope you've seen in the news that JWST has finished its construction in Southern California. It's been all folded up, as shown here at the top center. It's been loaded into its shipping container at the lower left, and it finished the transit by boat through the Panama Canal and has now arrived in French Guiana, where it's going to be launched on a European Ariane rocket, target date December 18th. So after years of being famous for taking too long and costing too much, JWST is finally going to be famous for great science. But the direct imaging of the front illuminated planet is really the future of the field. This is the recommended approach that the National Academy of Sciences Exoplanet Science Strategy Report will see pursued in their 2018 description. And this is advantageous because instead of combining the light that's passing through the planet's upper atmosphere with all the other light of the star, we're separating the planet light from the star's light. We're blocking it with a starlight suppression system so we can see the planet's light without all that extra noise. And the imaging method is sensitive to planets all over the region in that planetary system, not just the ones that are preferentially aligned to transit. Transiting planets in the habitable zone, only like 1 out of 200 planets is going to be actually aligned for transit. All the other ones are going to be inclined and not pass in front of the star, but for imaging, that's not a problem. We can still detect those. We can see the entire planetary system at once with imaging, including dust that may be associated with asteroid and Kuiper belts. And it's uniquely capable, a space-based direct imaging mission, of taking spectra of Earth-sized planets around sun-like stars. Careful consideration of this has shown that JWST won't be able to do this, and neither will the large 40-meter telescopes and 30-meter telescopes being planned for the ground. They will have a niche to look at small red dwarf stars, however. So let me talk to you about an example of why we need to go to direct imaging. There's a nearby star system, a triple, called 40 Eridani, or Eridani is a constellation. And in that system, there are 3 stars. Star A is a sun-like star. Stars B and C are orbiting each other well separated away from A, so we can effectively ignore them in considering our ability to detect something around A. Okay, so the habitable zone around star A is at a separation of 0.1 arc seconds. I'll remind you, an arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree. So this is a very small angular separation between the planet's orbital elongation and the star. So we can calculate how much of a wobble on the star's radial velocity it would produce, what the chances are of it being aligned for transit. The star has already been surveyed and no transiting planets have been seen so far. There's the cousin of the radial velocity technique, the wobble in the stellar position, called astrometry. That is too small a signal also to detect. So right now we can't look at this nearby star and see if there's a planet as fantastic as the Earth present or not. Well, this is the host star of the fictional planet Vulcan. And I really want to drive home the point that we just haven't ever developed and deployed the observational methods that would let us detect a planet in the habitable zone like Earth around the star. So if we're going to be able to search for Spock's home, so to speak, how are we going to actually be able to do it? And it is through imaging, because if you go to imaging, the planet in that habitable zone would have a magnitude of 27.6. You probably heard about first magnitude stars as very bright ones. The human eye is limited to 6th magnitude that it can see at a very dark site. Well, this magnitude 27 sounds faint, but it's actually something that Hubble could readily detect. Hubble's a 2.4 meter telescope. This planet would also be separated from the star by about 3 resolution elements. So we're able to go and see the resolution of Hubble, where a telescope modestly larger than Hubble can actually see this planet too. And of course, we can collect the photons with the direct imaging to do spectral measurements of the atmosphere. So we don't need much bigger telescopes than Hubble to be able to do this kind of star and detect and characterize its planet. The main advance that needs to happen is to be able to detect the planet that's 3 billion times fainter than the star in reflected light. That is 1,000 times beyond what Hubble can do. So at NASA JPL, we've been working on this problem for more than 15 years. We have a set of laboratory test beds, vacuum chamber shown on the left. Inside is an optical bench with a simulated star, an instrument called a coronagraph that can block that star, and a detector that shows us how well we're suppressing the light of the star to allow a planet to be seen. The image on the right is an image of the field of view around the blocked star, which is at the center. And the thing to notice is the colors inside the annulus there. They're mostly down at the -9 and -10 level, which is our contrast that we're aiming for, 10 to the -10. So we've demonstrated raw contrast performance in the lab of 2.5 billion to 1 at the relevant separation. We want to be able to see Earth-like planets around nearby stars in their habitable zones. So we want to turn that high contrast lab technology demonstration into a mission. And a couple large mission concepts have been developed for that. One of them is called HABEX, the Habitable Exoplanet Observatory. That's a 4-meter telescope based on a single monolithic mirror. It would have instruments to be able to detect and characterize the planet. It would use both a coronagraph inside of it and a free-flying star shade to be positioned between the telescope and the target star. It's another way of blocking the star's light. And utilizing these both actually gives you more return than any one individually. It would need a large launch vehicle, and it could be a mission selected and then launched in the mid-2030s. The larger version of this, also to turn our lab demo into a mission, is called Luvoir, the Large Ultraviolet Optical and Infrared Observatory. It's got 2 different versions, a 15-meter really large version. I'll remind you, the largest telescopes we have on the ground right now are about 10 meters. And it's got a more modest 8-meter version, still bigger than HABEX. And this would give you ability to go and detect several times more habitable zone planets than HABEX would be able to do. So you can take your choice between these various options. How many planets do you want? How much stomach do you have for the technology risks and for the cost? And these are the kind of spectra that you would hope to be able to get with planets observed by either one of these telescopes. The smaller telescopes would require more integration time to get the spectra that are shown here. And you can see they range from gas giants at closer to the star than we have in our own system to spectra of the Earth at different points in its history. And there are transitions in the Earth's history where we go from methane and carbon dioxide dominated down to water and oxygen dominated today. So we can gauge the state of evolution of the planet's atmosphere also from the composition. Now I want you to know there's an imminent decision coming up on the future of US exoplanet missions. You probably know that Planetary Science is doing a decadal survey right now. And in 2022, they're going to issue a report from the National Academy of Sciences saying, what are the priorities for future planetary exploration for 10 years? And of course, we're all hoping that Mars is prominently in there. Well, the astronomy decadal survey is running late, partly due to COVID slowing everything down. And these HABEX and Luvoir mission concepts were submitted for consideration as NASA's next large space telescope mission, along with an X-ray observatory and an infrared observatory. So is now the time for a big NASA exoplanet mission? It's hard to say, because the decadal survey has to weigh the priorities for all different areas of astronomy, cosmology, black holes, etc. So I don't know if we'll rise to the top, but we have some advantages this time, because since the last decadal survey, Kepler has shown that there are lots of exoplanets out there. We don't have to doubt that there will be a great number of targets. And of course, the idea of exploring nearby stars to see what their planetary systems are, targets for eventual future exploration. That's an idea that has a lot of resonance with the public.
You've got 5
So,
minutes left.
right, okay, so let me just finish up quickly and say the NASA Exoplanet Exploration Program, our existence is to enable these kind of missions in the future and to support the current missions that we have right now. And our job is really kind of interesting. Discover planets around other stars, characterize their properties. Well, let's explore strange new worlds. Okay, identify candidates that could harbor life. Well, that's seek out new life. So I think that's as close to the Star Trek opening motto as you could get and still be doing real science. And so our program has a number of different things that it does. The technology development is probably the most important, getting that high contrast imaging capability ready with star shades and coronagraphs. We also may be familiar with our communications products. We have a series of Exoplanet Travel Bureau posters that have proven to be very popular. I see them all over the country when I travel, as well as supporting ground-based astronomers in their follow-up of Kepler and TESS and other missions. So here's kind of a timeline. On the left-hand side in the blue are the missions that we have now or the missions that are in work to launch in the 2020s. And on the right-hand side are the potential missions that the Decadal Survey could choose. And so the science that these enable changes as you go to the bigger missions, because now we can discover habitable zone exo-Earths. We can potentially discover biosignatures by seeing both oxygen and methane in chemical disequilibrium in the same atmosphere at the same time. And so this is something that the European Space Agency is interested in just as much as NASA. We expect to partner if a large mission is selected. The last slide, as I just wanted to show you, I think we've got a historical progression of exploration here. When Galileo turned his telescope at Jupiter and saw the Galilean satellites for the first time, Jupiter went from a planet to a system of worlds. Okay, well, we have actually been able to accomplish that in our ground-based observations of very hot young planets. Here is a star you may have heard of called HR 8799. Has 4 planets, very massive, about 10 Jupiter masses, very young and hot from their formation. We've actually been able to watch them orbit around the star. Well, we are aspiring to do that for the interplanetary systems with small planets like the Earth around nearby stars in the late 2030s with these future missions. And so I hope you can be as excited about that as I am about Mars exploration. And I welcome your questions and discussion. Thanks.
Thank you, Dr. Stapelfeldt. Lyra, do we have any questions in the Q&A panel?
Yes, we've got a couple of questions. So I'll start with the one from Evandre. And they say, they ask, how accurately can we measure the density of the atmosphere on exoplanets?
Well, that's going to depend on taking a spectrum and then using a model to back out what you think the density is. And the density of the atmosphere is not just one number, it varies with height. So you're really asking how well can we derive the atmosphere's structure? So I think the biggest thing we'll be able to work out is what is the surface pressure. We should be able to tell that a planet has 1 bar of Earth atmosphere level or many bars, many times the Earth atmosphere surface pressure. And then the abundances of chemical tracers as well.
And we have 1 minute for probably one more question. Let's see, how long would it take to reach a similar planet to Earth, habitable planet from Mars with current or predicted space travel and technology?
Well, it all depends on your optimism for space travel technology and whether you're going to allow yourself relativistic effects so that it doesn't seem as long to you. But this is, quite a very long time in the future. But I'm convinced that in order to inspire people, engineers, to develop the means for interstellar travel, we've got to present them with exciting targets to explore. And we're going to find those with these kind of telescopic missions that I've described to you here today. So let's get started. Let's find our destinations, our first destinations for interstellar exploration.
Yeah, thank you very much, Dr. Stapelfeldt. Very fascinating.